Hello and welcome to our training session on PLAXIS LE. My name is Marina Trevisoli and I will be walking you through the use of searching techniques in the limit equilibrium method. An overview of the presentation today is as follows. We will start with an overview of what is the problem and then review the various searching methods implemented in the software. Only methods implemented in 2D will be considered in this presentation. We will finish up with a review of 2D spatial searching within the context of a 3D conceptual model through the multiplane analysis method. For the classic method of slices, the slope is divided into a number of vertical slices, and the bottom of each slice ends at the current analyzed slip surface. The slices then analyzed with respect to moment and/or force equilibrium will calculate a resulting factor of safety. However, the method requires a trial and error procedure to try to identify the slip surface that yields a minimum factor of safety. Such a trial and error process can yield hundreds or thousands of trial slip surfaces, which must be evaluated. The factor of safety calculations can consider circular, opposite, or non-circular shapes. In early efforts in 1920, John Hanson promoted the use of the Swedish method and noticed that many slip surfaces were often circular in shape. Therefore, early attempts to numerically model a slip surface were circular. It has been found that a number of scenarios can also yield slip surfaces which are non-circular. Weak plains, bedrock, rock faults, or undrained clay layers can all yield conditions which result in non-circular slip surfaces. Therefore, the software must be comprehensive in considering both circular and non-circular trial surfaces. Circular slip surfaces are generally quite easy to search for. The methods for searching for circular slip surfaces have been well developed in research, and a number of methods are implemented in the software, such as grid and tangent, entry and exit, grid and line, or automated method such as slope search or auto refine. Non-circular slip surfaces represent additional challenges in identifying the minimum factor of safety. The software has implemented a wide variety of non-circular searching methods, such as the block search, the Greco and PATH methods, and the dynamic programming method, which is based on a related stress analysis. The methods therefore provide a comprehensive suite of searching methods to find a minimum slip surface. It should also be noted that we are increasingly being asked to deal with such problems as geomembranes, rock fractures, and thin clay layers in analyzed geotechnical problems. The searching method becomes therefore one of the more important aspects of the analysis to consider. Research has shown that the difference between analysis methods in various software packages should only vary approximately 1.5%. However, changing the search method can easily vary the factor of safety by plus or less 20%. Therefore, the searching method with limit equilibrium becomes a critical part of the analysis. It is recommended to try a few different search methods, both of manual origins and automated, to have a higher chance of identifying the critical factor of safety. A particularly challenging aspect of finding slip surfaces is when geomembranes are present in earth structures. In this particular case, a geomembrane is placed between lifts of material in a heap leach facility. However, the shear strength of the geomembrane is significantly less than surrounding material and therefore creates a preferential shear pathway. Sliding along the geomembrane must be considered in the analysis. Likewise, it can also be demonstrated that pore water pressures can build up in front off or behind the geomembrane in a model and can create adverse pore water pressure conditions to consider. Therefore, the ability to search for a slip surface around the structures, such as geomembranes, is important. Other examples we can look at are thin clay layers, such as those that may be present in an embankment or underneath a railway or roadway, or in the thin layer present in the mining waste rock piles. The searching algorithm must be able to identify and follow preferential weak layers that may result in critical slip surface. Traditional circular searching methods include the grid interradius method, the grid in point method, entry and exit, and slope search. All of these methods can be robust. However, the user should be aware of searching for boundary cases at the edge of the searching limits. The search zone may have to be expanded to include all the possibilities. Also, if materials have no cohesion and slip surface will tend to rise to the ground surface and shallow failures will be preferential. Some cohesion is often required to be entered to realistically represent slip surfaces that are not shallow. Unsaturated sections also act like cohesion and tend to remove the risk of shallow slip surfaces. The The grid and radius method shown here offers a tried and true method of searching for circular slip surfaces. Automated methods such as slope search and auto-refine are easier to use and require less user input. Often the automated methods may not always yield a critical slip surface and should not be used exclusively. The slope search randomly generates the first point, and then a second point between the first point and the right limit. A center point is then calculated based on the first point, an initial angle at the 2 is used to calculate a potential slip surface. The method requires very little user input and can be used in conjunction with more manual methods. It can be seen here that the slope search provided a wide variety of slip surfaces that transact the slope and on in a similar slip surface, but one that is not quite visible is minimum as the gradient radius method previously displayed. It's also noted that the searching method is somewhat broader across the slope and may catch trial slip surfaces that would be missed by the grid and radius search. The auto-refine search is another automated method for searching for trial slip surfaces. The procedure is outlined as follows. The slip surface is divided into a number of divisions according to the division specified along the slope. Then, slip circles are generated between each pair of divisions according to radius input. The factor of safety are then calculated for the slip surfaces and the average factor of safety associated with each division along the slope is recorded. This constitutes one iteration of the auto-refined search, and in the subsequent iteration, the percentage representing the lowest factor of safety of the divisions is used. For example, in the auto-refined search, there may be 10 divisions along the slope, and then 50% of these divisions are used in the subsequent iteration. This will result in 5 divisions, which will be used, and the other 5 divisions with higher factor of safety will be discarded. The selected divisions in the previous step are used to form a new polyline and repeat steps 1 to 4 until the number of iterations are satisfied. If we apply the auto-refine search to our current problem, we see the variety of slip surfaces that are generated, which is slightly different than either the slope search or the grid and radius method. The factor of safety calculated is in a similar location and is close to the previous factor of safety, but is slightly higher. So to summarize, the circular methods are quick and easy to use, but there's often no guarantee that the slip surface is circular. So it should be noticed that this is especially true in the case of heterogeneous models. Therefore, in some models, it is good to engage in non-circular slip surface searching algorithms, such as the block search, fully specified search, path search, Greco search, or to utilize the dynamic programming method. The block search is ideal to use in cases where a particular weak sliding path is known, such as in a heap leach facility with a geomembrane, or in cases where failures of blocks along non-fracture zones is considered likely. In this case, the slip surface can be searched through a variety of hinge points, including block search zones, points, or fracture polylines. A slip surface can be fully specified by the end user, which it is often ideal when doing back analysis of a known failure where certain key points of the slip surface are known. A number of slip surfaces that are specified can be tried in the same model run. The path search forms a powerful non-circular searching method. In this method, a starting point is randomly generated on the slope surface based on slope limits. It is also possible to use the method with two different sets of slope limits. Starting from a first point, the first segment is randomly generated according to the initial angle at the tool, and the segment length is specified. The subsequent segments are randomly generated according to the segment length in the previous segment angle. The method is restricted to only generate concave surfaces. Calculations continue until the segment intersects the ground surface, and if it is within the slope limits, then the surface is valid. Steps 1 to 4 can be repeated until a valid number of trial slip surfaces has been generated. This example shows the use of path search to generate a non-circular slip surface, which particularly follows a weak layer. The model which demonstrates this method may be found under the slopes group available under the PLAXIS LE Manager. The Greco search is also a powerful line segment-based searching method that uses random number of generators to generate points and subsequent line segments. It also forms the basis for the optimization longer than utilized in the software. The Greco search has the ability to follow weak surfaces. Its ability is largely dependent on the random number seed utilized, and therefore the user should experiment by changing the seed to different values. The dynamic programming method is often confused as an analysis method, but it's fundamentally based on a series of line segments which are generated through a stress field. The stress field is generated by a finite element analysis in which gravity is turned on. The factor of safety definition is the same as in limit equilibrium. The method essentially uses the traveling salesman algorithm to find a minimal slip surface through the stress field. The factor of safety is minimized, and there is no requirement that the slip surface be circular. Optimization can also be added in the software to any circular or non-circular searching method. The optimization is based on the Greco method and takes an existing slip surface and subdivides it into line segments. Each vertex in the line segments is varied to see if a lower factor of safety can be obtained. The example below shows an analysis where a circular slip surface finds a factor of safety of 1.1 and is subsequently optimized to obtain a slightly different slip shape and a lower factor of safety value of 1.0. Therefore, the method is powerful in optimizing to a minimal critical slip surface. An important aspect of searching for a critical slip surface is searching spatially in the context of a 3D site plan. It is possible to search for a critical 2D section within the context of a larger site. This functionality is termed a multiplane analysis in PLAXIS LE software. The analysis is easy to set up and planes are automatically created perpendicular to the most downslope direction at the site. Each plane is a comprehensive 2D limit equilibrium analysis. After all the analyses are run, the 2D slip surfaces are displayed along the critical planes in the context of the original 3D model. The multiplane analysis feature may be enabled under the Model Settings dialog. Once the feature is enabled, then the remaining configuration for the multiplane analysis may be set up in the model. Multiplane analysis dialog will be enabled. The primary input data utilized for multiplane analysis is to create planes that cover the searching area of interest, to create a center point and length of each plane, and to define the searching parameters along each plane. The multiplane analysis dialog is shown in the right-hand figure. On the left-hand tree view is a list of the individual 2D planar models created. Multiply lists can be created and they are automatically grouped by the actions that create the group. The right-hand options are only applied to the selected planes. It is also important to note that further assistance can be found under the Help button. There are two primary methods for entering analysis planes. The user can enter multiply planes at once from either an elevation counter, which is probably the most common, or based on the entry of a polyline drawn across the topology of the model. It is also possible to enter individual planes on a model by drawing them graphically or entering the plane from coordinates. When the user selects to enter automated plane generations, they select the distance between the planes, as well as the amount of surface smoothing to consider in order to calculate the downhill direction. A decrease in the surface smoothing strength number allows capture of smaller features on the topology. The most common method of generating planes is based on an elevation counter line. In this method, the user will click a location midway down the slope on a section. The elevation will be highlighted graphically on the screen, and planes are created at every point in the slope at that elevation by following the elevation line laterally. The user can optionally constrain the lateral movement to a maximum distance from the picked point. It is also important to note that the planes are automatically oriented to point downhill, and this can be later adjusted. It is also important to note that the user can specify for the critical slip direction to be searched based on a range of values. The user can also create planes based on a polyline. The polyline can be drawn laterally across a three-dimensional slope and midway down the slope. Polyline points can also be pasted in from PLAXIS Designer. Planes are drawn along the line in the most downhill direction. Lastly, planes can also be created manually by either drawing them by the user or entering coordinates to define the plane. This feature is useful for covering small features or very specific parts of the topology. The Slice Data tab is used for adjusting geometry parameters of the selected planes. The user can set the search limits on each plane, which limit the extent to which trial slip surface will be selected. Selected planes should include the search area of interest on the slope. By default, the method picks the most downhill direction at each point in the slope. There is no guarantee that this direction is the critical direction for the critical slip surface. Therefore, it is recommended to enter multiple orientations for the software to search for the critical slip direction. Three angles is perhaps a good start, and obtuse geometric features such as bull noses are excellent candidates for a wider sweep of slip angles with additional increments. The Search Method tab sets the slip surface searching method for each of the selected planes. In 2D, the user has the option of a number of selected methods, including entry and exit, slope search, and the Kukul search. The number of trial slip surfaces will have an impact on the ability of the software to find the critical slip surface. It should also be noted that it's possible to enable optimization such that a circular shape can be optimized into a non-circular shape at any specific location. As suggested procedure for using the multiplane analysis, subdivide the overall site into sections. Then define plane locations and directions generally from an elevation contour for each section. Then adjust the slope limits to constrain the searching extents. It is recommended for the first pass to set the common searching parameters for all planes at once. Once critical zones are located with the first pass analysis, it is possible to adjust as needed for each section group. Some sections may need fewer trials or more angles to improve the accuracy of the result. The user is free to adjust as needed for each plane or spatial location. For example, planes along non-likely or critical locations can be given for more trials to increase accuracy. So, to summarize the searching methods, circular methods are fast but do not often yield a global minimum. Automated circular searches are simple and automated, but do not necessarily yield the critical slip surface as well. Therefore, both automated and non-automated methods should be used for searching. There are fewer non-circular search methods in the software, but they remain powerful in determining reasonable non-circular slip surfaces. Dynamic programming is the only theoretically based searching method in the software and is a powerful method. And lastly, optimization can be used to further refine circular or non-circular shapes. Multiplane analysis is an effective manner by which the spatial location of the critical slip surface can be determined in a 2D fashion. Thank you for your time in performing this training on the software.